Hoping that's a good sign. Y'all do have a test due next week. Don't forget, or actually, it's already available. It's been available. You could have done it just about any day this week. No one asked me to, but I did have one student ask to do it on Saturday. And I pushed the deadline back until the 8th, which is Wednesday of this coming week. So you have to get it done by Wednesday at 11:59 p.m. It has to be proctored. If you get it proctored at this testing center on any of our campuses, that's free. You just might have to make an appointment, and you need to call them and find out what their rules are. Anybody have any questions on any of that?
I have kind of a brief question.
Yeah, go for it, Noah.
So, do you make the quizzes that are on Canvas?
Yes, I make all the quizzes and practice tests and chapter tests and the actual tests as well.
So, those actual tests that we're getting in person are also made by you in that same format?
Yeah, that's part of the reason why I give you the practice test, and that's also I sort of tried to spell it out in the syllabus. The practice test that you take, I guarantee that the actual test that you ultimately take will have 90% of the points on that test from questions that were available to you through those practice tests. That being said, I have not added any questions outside of that test bank in probably 12 years. So it's literally 100% of the questions. So if you, in principle, did every practice test an infinite number of times, then you will never be surprised by seeing a question you didn't already see.
Okay, thank you.
No problem.
Um, for
Yes.
the you said it was open book and open note for the
For the online and for the practice, but not for the
not
face-to-face
for the
test.
in-person. Okay.
Yeah.
Um, I signed up for the for it and I got scheduled for Tuesday or yeah, next Tuesday,
Okay.
but I didn't specify it had to be proctored. I didn't know that part. Did I need to specify it has to be
Oh
proctored?
no, if you got it at the testing center, it's going to be proctored. You sit somewhere and they have a computer that watches that they're allowed to watch your screen on. It's locked down so you can't access any websites, and they've got a camera on you.
Okay.
So
All right.
yeah, it should be proctored. And I've also sent them the information so they know not to give my test unless people are proctored.
All right. Okay. Thank
No
you.
problem. Anybody else? All right, so just reiterating, y'all can feel free. It looks like most of you already done so, but feel free to go ahead and chat me your first and last name so I'll have you for attendance. I did mention that I've moved the due date for the first face-to-face test from this Sunday at 11:59 p.m. I moved it to Wednesday, in other words, a week from today at 11:59 p.m. So you have a little bit more time. That seems like it might be necessary because I just Colin said he just got a appointment for Tuesday of next week. That makes me think that maybe that was uh, what they had available, in which case we might be running out of appointment times. We also have, in addition to the appointment times that you can make at the testing center, I'll be administering a test at face to face on Thursday, excuse me, on Wednesday and on Thursday of next week. So in principle, you could come to the Virginia Beach campus and have it scheduled where I would proctor you. So that's another option for you if you run out of time, but you would have a very specific time that you'd have to be here. Specifically, I think my tests are going to be Thursday. You'll need to confirm that with me via email, but I think my tests are supposed to be on Wednesday and Thursday, and I want to say the 241 one starts at 12:30. It's either 12:30 or 1. I'll double check that for the Wednesday 241. And then there's another time at 3 o'clock, or excuse me, at 2 o'clock on Wednesday. And then there's another time, I believe it's Thursday. And in that case, that would be at 9:30 in the morning. So those are all available to you guys too if you wish.
Wouldn't the Thursday appointment be out of our time frame?
It would, but if you can't make an appointment in time and that's your last option, then I'll allow you to take it on Thursday as well.
Okay,
Yep.
thank you.
It's not the plan, but like I said, if you just can't get another one and you want to take it on a Thursday, I'll be glad to do that. And I'll give everybody that option, including if they want to take it at the testing center to Thursday, I'll just push the deadline back to Thursday. I got to double check though. I can't. I'm pretty sure I made my 202 test, which meets on Thursday. I'm pretty sure I made that Wednesday, but I mean Thursday, but I might have made it Tuesday. So once I confirm that, I'll let you guys know. Sorry about that. Anybody else have any questions? All right, so make sure you get all those online tests done. I did get some emails from actually weird thing. I got like six text messages from a student yesterday, and they all came yesterday, even though I could tell one of them was sent. He said it was on a Saturday, so that was sent some Saturday ago, and I don't even think it was this past Saturday. I think it might have been the Saturday beforehand, but it literally didn't get through to my phone until yesterday. Plus, he had some more that were earlier in the week that he had sent me as well, and I didn't see any of them. I don't know if it was a Verizon thing. That's the cell carrier I use, or if it's maybe one of their cell carriers, or something's wrong with my phone, or what. But I've got to work with that student because they missed some deadlines as a result, partly of me not being able to reply to them. So keep that in mind. I'll do my best to listen. Also, if you send an email to me and you don't get a response within the 24 hours, like I spelled out on the syllabus, go ahead and send me a text message at that time so you can let me know. I've never had, well, actually, once before I've had this happen where I got a text message like a couple days after it was actually sent, but that's only happened once before this time. So I don't think it's very common, but it does occasionally happen. All right, so I guess we're going to go ahead and get started. Last time we worked basically a bunch of friction problems, and those are the crux of Chapter 5. However, there's another branch of Chapter 5 that's about the beginnings of rotational motion and specifically motion in a circle. So I wanted to start off by offering you guys an extra credit problem. Because normally what I do is I tell students to do this and then they come back the next day and they've supposedly already done it. So I'm giving it to you as an extra credit problem. Let me go ahead and share my screen so you'll know. And of course, the video will be posted so you can take a screenshot of this if you'd like. That way you'll have a screenshot of it. But if you feel like you still need, oops, I'm looking at the wrong thing. If you feel like you still need to see it, then just go and pull up the video and on my YouTube channel and see it. But here it is. I've written it out. I'll read it out loud to you because I know not everybody reads cursive, and I mainly write cursive because it's a little bit faster. So consider the vector function r equals capital R times cosine of parenthesis 2 pi over capital T times lowercase t. The lowercase t is actually considered to be in the numerator, for instance, close parentheses I hat plus r times the sine of parenthesis 2 pi over capital T times t close parenthesis times j hat. Again, that t is also quote unquote in the numerator. The lowercase t is the time variable, and the uppercase T is a quantity we call the period of the revolution. So I have a circle drawn here, and it looks like a circle of radius 4 units, whatever the heck that is roughly. But the main thing is we're imagining taking off at the point x equals 4, y equals 0, and then going up to the point y equals 4, x equals 0, and then to the point x equals negative 4, y equals 0, and then to the point y is negative 4, x equals 0, and then back to the point x is 0, x is 4, y is 0. The time required for it to make that full circular trip is called 1 period, and that's represented by the letter capital T. The R capital is representative of the radius of that circle. And it says where R and T are constants, R being the radius of a circle and T being the period of revolution for the object imagined to be revolving in a circle of radius R about the origin. A, for extra credit, make a table of the coordinates x comma y defined by R for t equals 0, capital T over 8, capital T over 4, 3t over 8, t over 2, 5t over 8, 3t over 4, 7t over 8, and t. You may define omega to be 2 pi over t, so that r function would then be r cosine omega t I hat plus r sine omega t j hat. But you can do that, and then also if you still don't like working with symbols, you can go further and make the capital T 8.00 seconds, and you can make the capital R 4.00 meters, specifically if you're uncomfortable working symbolically. You can do this whole thing symbolically, and it's much, much better to do it that way. But like I said, if you get a little confused, just punt and put those numbers in, or even like I said, just calling that thing omega might make it a little easier. Don't forget your chain rule. When you take the derivative of R, you don't have to do any derivatives on the I hat and J hat, but you will have to take the derivative of R cosine omega T, and that's the derivative with respect to time. So it becomes negative R times times sine of omega t, and then you got to take the derivative of omega t with respect to time, which is omega. So the x component becomes negative omega r sine parenthesis omega t close parenthesis I hat. Similarly, when you take the derivative of the y component, that's going to become positive omega r cosine omega t close parentheses j hat. So that's the big trick there. I actually just spelled out the first part of this extra credit for you. Then for part B, notice I did make the table to the right. So that's that table, or excuse me, to the left. That table that you see to the left under the circle, the middle column is where you're supposed to put the value of x for each of those times, and the far right columns where you're supposed to put the value of y for each of those times. And then you're going to be asked to actually write down or draw the vectors for each of those 8 times for the radius. Then what I'm actually asking you to do is choose the 0, the t over 4, the t over 2, the 3t over 4, and the t for the velocity vectors, and do the same thing for the acceleration vectors. You'll see that's in the other parts. So part B, I say compute v equals dr dt, and then compute the magnitude of v. And I give you a hint, the magnitude of v is actually a constant. You're going to have to use a trig identity to see that work out to be a constant, but it should come out to just be a constant. C, compute a, which is equal to dv dt. So when you get that v in part B, the v vector, when you get that vector function, you take the derivative of that with respect to time, and that'll give you the acceleration vector as a function of time. And then I ask you to calculate the magnitude of A. I didn't put the note there like I did with the V, but it turns out the acceleration is going to be a constant as well, again, once you use the trig identity. Then you get to part D, and I tell you to plot 8 R of T's, in other words, one for each of the 8 times that I said, 4 V of T's. That's where I'm telling you to skip every other one. So you do the 0, you skip the T over 8, you do the T over 4, you skip the 3T over 8, you do the T over 2, you skip the 5T over 8, you do the 3T over 4, and then you skip the 7T over 8, and then do T. And then 4 A of T's, the same ones again on the circle drawn above. Finally, in part E, use V, the magnitude of the vector V, to write A, the magnitude of the vector A. That's actually supposed to be just the plain magnitude. Let me fix that real quick. You're asked to do that magnitude of A, express that in terms of V and R. So in other words, you're going to find an expression for V that's the magnitude of V, and you're going to find an expression for A that's the magnitude of A, and the expression for A is just going to have omegas and R's in it. And what you want to do is eliminate the omegas and just represent it in terms of V and R. So when you do that, you'll have completed the derivation of the formula we're getting ready to use. That's why I gave you this as an extra credit. That's also part of the reason why I went ahead and told you exactly what the derivative of r, the vector, would be. I'll repeat it again, and again, it's on the recording too, so you can always check the video. But dr dt, the vector function called the velocity as a function of time vector, is going to be negative omega r cosine omega t I hat plus omega r sine, or excuse me, that was negative omega. Let me repeat that because I actually said it backwards here. So the derivative of r with respect to t is v, the velocity vector function, and the x component of that would be negative omega r sine omega t, then times I hat, plus omega r times the cosine of omega t times the j hat. That's the actual derivative of r as a function of time as a vector. So that's me showing you how to do it, as well as showing you how to write it, as well as showing you how to do the chain rule. So at least you can parse out those words and make the symbols. But that's what you're asked to do for an extra credit. This is an extra credit, so it only counts as extra credit, but you would be crazy not to, because this is, a chance for you to actually do a derivation. Now I'm going to flip to the next page and write the result that we got. So the result, if you actually did that extra credit, what you'd find is the magnitude of V is actually equal to R times omega. And actually, I shouldn't write that as a vector symbol. I should write that as just plain V here. So I could write it V with a vector symbol, but then I have to put absolute value bars around it, or I could just write it as V like that. That's one of the results we got. The other result we got was the acceleration magnitude is actually equal to omega squared r, which you can then use V equals R omega to eliminate the omega, and you'll get a different version of A. But I'm not going to give you that part. I'm just going to say that's equal to A. So that's two of the results we're going to get. And in fact, ultimately, we're going to use A is equal to V squared over R, which also you can tell is equal to omega squared r. So those are two versions of the centripetal acceleration. So centripetal acceleration. So what I mean by that is, notice, because we learned that that vector function that I gave you had a constant magnitude velocity, then what we've found is the velocity or an orbit that goes around a point in a perfect circle with a constant speed v requires a very specific acceleration to keep it in that circle, and that acceleration is called centripetal acceleration, and it's given by the square of the velocity divided by the radius of the circle, or it's given by omega squared times the radius of the circle, where omega is a couple different words for it. Omega is sometimes called the angular velocity because it'll have units of radians per second. It's also called the angular frequency, uh, and it's given by a couple of different equations. The equations are omega. I don't know why this is doing this. Omega is equal to 2 pi radians divided by the period. That's one way of writing it. And I'm using the word period because we already defined that on the previous page. But we can also write it as 2 pi times the frequency. Now that frequency is the frequency that you might be familiar with. It's measured in hertz, whereas this one is the angular frequency, and therefore is measured in radians per second, or it's sometimes called the angular velocity. And it's also measured in radians per second. Now, in addition to that, there's a formula that relates the frequency to the period, and the formula is frequency equals 1 over the period. And period, by the way, has as its unit seconds, is the normal scenario. Now, your book goes a little bit further and talks a little bit about the kinematics of circular motion. So I just want to make a quick parallel to that. Our equations that we got from kinematics, that was chapter 2 and a little bit chapter 3. That was one dimensional, and of course, chapter 3 was three-dimensional, or at least two-dimensional kinematics. And the equations that we found were, for instance, speed average is equal to distance traveled divided by time taken. That's the average speed. The average velocity, again, one dimension here, so we're ignoring the vectorness of it, is delta x over delta t. And of course, that meant the instantaneous velocity was equal to dx over dt. Similarly, the average acceleration was delta v over delta t, and that meant the instantaneous acceleration was dv over dt. And you can make vectors of those as well if you wanted. Once we had those, then we were able to form these equations. The first one being x is equal to 1 half at squared plus v0t plus x0. The second one being v squared is equal to v0 squared plus 2ax minus x0. And then the third, which I rarely talk about, that is v bar is also equal to v0 plus v1 over 2. The big deal being that these three are only true if a equals a constant. Okay? Now, why did I do all this? Well, that's because there's another quantity called rotational, or another area of science called rotational kinematics. And oddly enough, the mathematics is identical. So we end up getting basically the following. V is played by a character called Omega, and Omega bar is delta theta over delta t. So you can see the theta plays the role of x. So in short, I could, for instance, list this as v becomes omega, and x becomes theta, and a becomes alpha. That covers most of it. There's actually more stuff to come. Got another student coming in. So now I'm going to continue with these definitions. So there's omega, and then omega instantaneous would be d theta over dt. We also have alpha average is equal to delta omega over delta t. And that means that alpha instantaneous is equal to d omega over dt. But here's the neat thing. Theta turns out to be 1 half alpha t squared plus omega 0 t plus theta 0. Omega squared turns out to be omega 0 squared plus 2 alpha theta minus theta 0. And then this one I've never, ever, ever used in my life, so I doubt you'll need it, but omega is equal to omega 0 plus omega 1 over 2. And again, these are for alpha equals a constant. Okay, so it turns out we're going to study rotational motion. I want to say it's chapter 8. I'm pretty sure it's chapter 8. When we get there, we'll be making use of this. But right now, you know the equations already, and it's so similar that you can literally take the wording of questions from chapter 1, and if you change the units of x from meters to radians, or preferably radians, but sometimes you could use degrees or something. And if you chose the change the units of velocity from meters per second to radians per second, and if you change the units of the accelerations from meters per second to radians per second, then you could solve that rotational motion problem in exactly the same way as you'd solve that linear motion problem. Now that we have that, I want to go ahead and show you how to solve a few problems. And I'm going to start off with example 5.8. So here we go. I'm going from the book now. This is example 5.8. And 5.8 says a 150-gram ball at the end of a string is revolving uniformly in a horizontal circle of radius 0.600 meters, as in figure 510 or 512. The ball makes 2.00 revolutions in a second. What is the centripetal acceleration? So I'm going to do like we did in the chapter 2. Remember, a good part of starting off in physics is trying to figure out, based on the wording as well as the units of quantities that a question gives you, try to figure out what symbol corresponds to each of those numbers. So, for instance, we have 150 grams. We know in the SI system we're supposed to be using kilograms. So that's going to be 0.150 kilograms. And the symbol we use for that is mass. So I'm going to put an M there. We also use, in this case, they've got the circle of radius 0.600 meters. So I'm going to use R, and I'm using capital R here, but you could use lowercase r. I'm just using capital because I can sort of differentiate that from the R that I use as a coordinate, if you will. So R is going to be 0.600 meters. And here's the one that might cause you to stumble a little bit. It says the ball makes 2 revolutions in a second. Well, if I were to explain to you exactly what frequency is measured in hertz, and that means cycles are revolutions per second. So when I say something is a has a frequency of 5 hertz, what I mean is it completes 5 cycles or 5 revolutions in a single second. So when this says a ball makes 2.00 revolutions in a second, that means F is equal to 2.00 revolutions per second, which is the same thing as 2.00 hertz. Now, by the way, this is the units on your radio station on the FM dial as well as the AM dial. On the FM dial, for instance, I listen to Bob 93.7. 93.7 is 93.7 megahertz. So that means million hertz for the FM 93.7. Whereas if you listen to AM, I often listen to 850 AM. That's where I used to listen to Michael Savage and Neil Bortz and G. Gordon Liddy and Rush Limbaugh and all that good stuff. That one is 850 kilohertz. So that's 850,000 hertz. But that's what those quantities are. And now that we have those all written down, we know that they're asking us for the centripetal acceleration. So a centripetal is equal to question mark. That's what they're wanting to know. So what we've done, if we carried out that derivation, or if you just take the results at the top of this page, you would know that we have equations for the centripetal acceleration. A is equal to v squared over r. R A is equal to omega squared times r. Either one of those is fine. What I see here is I definitely have an R, that's fine, and I definitely have an F, but none of these equations have F in it. So what I could also do is say that omega is equal to 2 pi times F. You can think of that as omega being 2 pi F is really just taking the frequency in cycles per second and converting it to radians per second, because one cycle in terms of circular motion is 2 pi radians around. So I'm literally converting from cycles per second to radians per second. If I choose to do that, then omega is going to be 2 times pi times 2.00 revolutions per second, because that's another version of saying what cycles per second is or what hertz is, I could also clarify by specifying specifically that 2 pi means 2 pi radians per one revolution. When you do that, then it makes a little bit more sense, and you can see what I was talking about the 2 pi times f just being a conversion. So if I take 2 times 3.14159 times 2.00, then I get 12.56. Let's call it 12.57, and that is in radians per second. So that's my omega. Now the centripetal acceleration is equal to omega squared r. So my centripetal acceleration, A centripetal, is equal to omega squared, which we found was 12.57 radians per second. That's one extra digit than sig fig. That's going to be squared. And then I'm going to multiply that by 0.600 meters. And remember a radian, if you remember it from trigonometry, a radian was defined as the arc length divided by the radius. And normally you'd use the arc length and the radius both measured like in centimeters or both in meters or both in inches. So the main thing to remember is a radian is actually just a pure number, and therefore you can throw away the radian unit as necessary. In this case, that's exactly what I'm going to do. So I'm going to take 12.27, or excuse me, 12.57, and I'm going to square that. And now I'm going to multiply that times zero point 0.6. And that gives me, in fact, 94.75. Actually, I should be careful with that. It's 748. So it's not smart for me to round it to 5 because that would make me round the 7 up when I shouldn't really do the 7 up. Because it only had a 4 next to it. So it's 94.748 meters per second every second is equal to the centripetal acceleration. Now, also what that means is if perchance you wanted to calculate how much force that string would have to sustain to keep that ball going in a circle, then from the summation forces is equal to mass times acceleration, we can see that the tension, which equals the summation of forces, would have to be equal to T is equal to 0.150 kilograms times 94.748 meters per second. And that gives you about 14. That gives me 14.21 newtons. So if you really wanted to know exactly what strength of string you'd have to be able to spin that like that, you need to make sure it can sustain a force of 14.2 newtons. Anybody have any questions on that one? All right, here's another neat little problem. This one is a problem that actually Newton solved, and it specifically says, this is example 5.9.
So real quick, can you go back to the previous problem for just a quick second?
Yeah, no problem.
Perfect, thank you.
No problem. There is another example later that they're going to ask, and that example is actually referring to what I just did with the green print down there. So just keep that in mind. I think it's like 5.11 or 5.12 or something like that. But here we are on example 5.9. It says moon centripetal acceleration. The moon's nearly circular orbit about the Earth has a radius of about 384,000 kilometers. So I'm going to write that figure down. Radius of the orbit is 384,000 kilometers. Now, we don't use kilometers in the SI system. We're supposed to use meters. So y'all can double check this, but it should be 3.84 times 10 to the eighth meters. So that's what my radius is. And they said, and a period T of 27.3 days. Now, days is not a unit we use either, so I'm going to have to deal with that. And they want me to determine the centripetal acceleration of the moon. So A centripetal is equal to question mark. Now, this is a particularly interesting problem because if you read Newton's Principia, he basically said something along the lines of, while sitting under a tree in my apple orchard, I looked up and saw a tree, saw an apple hanging, and in the distance, I saw the moon in the sky. And at that point, he realized the similarity between the moon and the apple. What he meant by that was having understood Newton's first law of motion, which he would have called Galileo's law of inertia. He realizes that the moon would tend to go at a constant velocity, therefore in a constant direction at a constant speed, uh, at all time unless acted upon by some net external force. But he knew for a fact that the moon sitting here by the earth turns so it gets closer to the earth, but not at a rate that actually makes it get closer. In fact, the earth more or less gets a little bit further away each time. But the main thing is the moon's changing direction constantly so it can continue to go in a circle around the earth like that. So there clearly had to be some force acting on it according to Newton's first law or Galileo's law of inertia. And he had studied light, and what he discovered in light was that, for instance, if you had a little candle lit and you had some way of measuring how bright that light would be 1 meter away, then he'd find a certain brightness. But then if he moved instead of 1 meter away and moved 2 meters away, he would find that the brightness at 2 meters wouldn't be one half as bright as the brightness at 1 meter, but rather one fourth as bright. 2 squared being 4. Similarly, if he measured the brightness of that light at 3 meters away, it wouldn't be one third as bright. It would, in fact, be 1/9 because 3 squared is 9. That's called a 1 over r squared law. So, just on a whim, he said, well, I know light does this. I wonder if the planets obey some kind of force pulling them to their moon or pulling them to their sun or something like that in a 1 over r squared way. So what we saw is when we went from a distance of 1 meter to 2 meters, we had to divide the strength by 2 squared, which is 4. If we went from 1 meter to 3 meters, we'd have to divide the old strength by 3 squared, which is 9. So it'd be 1/9. And if we went to 4 meters, it'd be 1/16, so on and so forth. What if instead Newton knew, for instance, that we on the surface of the earth are 1 earth radii from the center of the earth? And he knew that the acceleration due to gravity on the surface of the earth was 9.80 meters per second every second. He also knew that the moon was, in fact, a full 60 earth radii from the center of the earth. So the 9.8 was one radius from the center of the earth, and the center of the moon was 60 earth radiuses from the center of the earth. So can anybody tell me what you'd need to divide 9.8 by if it was a 1 over r squared law? Remember, we divided, in the case of doubling the distance, we divided by 2 squared. In the case of tripling it, we divided by 3 squared. So what do you think is going to happen to the 9.8? What are we going to divide it by when we go from 1 Earth radius to 60 Earth radius? Radii. Anybody? I'm trying to put my chat up so I can see. So far, I'm just seeing attendance. Anybody?
Can you repeat the question again, but in different wording?
In different terms. Okay, so Newton was considering the idea that the acceleration of the moon towards the center of the earth, which was supposed to be keeping it in a circular orbit, he was considering whether or not that was a force that went like 1 over the distance squared. And what I showed you as an example of 1 over distance squared was when the light was 1 meter away compared to 2 meters away, I would take the brightness at 1 meter and divide it by 2 squared, which would be 1/4. And if I went to 3 meters away, I'd divide it by 3 squared, which is 9, and so on and so forth. So, what would you think you would want to divide the 9.8 by, since the Earth is 60 Earth radii from the center of the moon? Colin and James are both right. Since we're going at the surface of the Earth, which is 1 Earth radius away, and we're wanting to consider what would happen to the acceleration at 60 Earth radii, we'd want to divide 9.8 by 60 squared. So that's what I'm going to do here. So Newton, I'll just write this real quick so y'all know what I'm talking about. Newton said a gravity, ultimately he called it gravity, okay, but a gravity at 1 Earth radius. This is the mathematical symbol that we use for Earth radius. It's R with a subscript 0 with a plus in it. That acceleration was 9.80 meters per second every second. And what we'd like to know is, what is the acceleration due to gravity at 60 Earth radii? Or I should say it like this. I'll say equals question mark. And what we found was it should be a gravity at 60 Earth radii is about equal to 9.80 meters per second every second divided by 60 squared, which is 3,600. And when you do that, you get 0.00272 meters per second per second. I'm going to double check on my calculator. 0.00272. Yeah, that's right. Okay. So that was what Newton did. Is he said, "Oh, well, if that's the case, if there is a force of attraction between the Earth and the Moon, and it falls off like 1 over the distance squared, just like light, then he would expect the acceleration of the Moon to be 0.00272 meters per second per second." Well, he had also invented the calculus and obviously could calculate centripetal acceleration just like we're doing. So that's what we're going to do now and see how right we are. First off, I'm going to convert the period from 27.3 days to uh, a certain number of seconds. So we know that, for instance, 1 day is equal to 24 hours, and we know that 1 hour is equal to 3,600 seconds. So we should expect the period to be, I'm going to take 27.3 times 24 times 3,600, and that's going to give me 2.359 times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the 6 seconds. Now, v, the velocity of the moon, is equal to 2 pi r divided by t. Remember, the 2 pi r is the circumference of a circle of radius r, and we're assuming the moon goes in a perfect circle, even though it's a little bit off from a circle, but a first order approximation, we're going to assume it goes roughly a circle. So we can calculate the velocity of the moon to be 2 times pi times 3.84 times 10 to the 8th meters, and then all that's going to be divided by 2.359 times 10 to the 6 seconds. And when we do that, it's 2 times 3.14159 times 3.84 times 10 to the 6. Oh, excuse me, times 10 to the 8. And now I'm going to divide all of that by 2.359 times 10 to the 6 in parentheses, and that gives me 1,023 meters per second. Remember, roughly 2.5 times that is the miles per hour. So we're looking at a couple thousand, 2,500 miles per hour, somewhere around there. That's pretty fast. Now that we have that, we can say the A centripetal for the moon is equal to V squared over R. So that's going to be 1,023 meters per second with one extra digit squared divided by the radius, which is 3.840 times 10 to the 8th meters. And lo and behold, I'm going to square this 1023. And now I'm going to divide that by 3.84 times 10 to the 8th, close parentheses, and that gives me, lo and behold, 0.00272 meters per second every second. So at that point, notice Newton did this calculation when he was alive, and at that point, Newton was literally the only person on planet Earth that knew exactly why the planets orbited the sun and why our moon orbited us. And it was because of this gravitas, which in Latin just meant a burden or a great amount of weight, a big heavy task, or something like that. So he called it gravitas, and that gravitas acted like 1 over r squared. Any questions on that one?
Um, I see it. That's how we got like how fast the Earth or the moon was moving based on like and he used like 9.8 for gravity. How did you figure out gravity was 9.8 meters per second squared? Because it's kind of hard to time that since it's accelerating and not going at a constant.
Exactly. So, what Galileo had actually worked that out, and Galileo didn't have a good clock. There wasn't good timepieces back then. They didn't have any piezoelectrics, and we're talking time intervals that were less than a second. So you couldn't use a pendulum or anything like that. What Galileo did was he made a clock that was a water clock. So basically, when you wanted to start timing something, you would open a stopcock, and water would start to pour into a container whose mass he already knew. And then when he wanted to stop timing, he'd turn the stopcock off and then he'd weigh the water. Now, he didn't have any idea how much time that was, but he knew, for instance, if the weight was twice as heavy as some other weight, then obviously that time took twice as long as the first one. The other thing he did was instead of studying motion that went straight up and down, he realized things moved too fast for him to see that. So he decided to study things rolling down and up inclined planes. And then you could use trigonometry to figure out the velocity or the acceleration that something had along the hypotenuse. How does that relate to the vertical component of it? And then that would allow him to get out the full acceleration, which was 9.8 meters per second every second. Does that make sense?
Yes.
It's
So
it's
admittedly,
not a
I don't
trivial
think I would
thing.
have had the patience for that myself.
Nah. But he was luckily going blind, and he was in house on in-house arrest, so he didn't really have anything else to do. But yeah, so he figured that out, and it was pretty ingenious of all those people. It's really impressive when you figure out how smart these people were. It's really scary impressive. All right. We've done 5, 9, and I would be inclined to try to do 5, 10, and stuff like that, which has a lot of stuff about, period and frequency, but really I need to get into the working of centripetal acceleration to use it for banked curves and stuff like that. The good news is, even if I don't get to that, there are videos that I posted in this week's module that shows me doing that derivation, but I'm going to go ahead and skip to a couple of those problems real quick. So let's look first off. Oh, example 511 was the one that I did down here in the green, so I'll write this down here. Let's write that in blue. So this green down here turned out to be example 11, where they asked us to estimate because they gave us exactly the same numbers. They said the ball makes 2.00 revolutions per second. The ball has a mass of 0.150 kilograms, and the radius of the circle is 0.600 meters. So all of that was exactly the same. So we were able to estimate that it'd be about 14 newtons. So that's example 511. I'm going to go ahead and jump to example 512 now. 512 is a little bit more complicated and it's not quite to the banking of curves yet, but it's still a good thing to use. So we're going to say example 5-12, and here I am reading it. It says a 0.150 kilogram ball on the end of a 1.10 meter long cord of negligible mass is swung in a vertical circle. Determine the minimum speed the ball must have at the top of its arc so that the ball continues moving in a circle. And B, calculate the tension in the cord at the bottom of the arc, assuming the ball is moving at twice the speed of part A. So I'm going to write down the information. We've got a mass is equal to 0.150 kilograms. I went ahead and made it into kilograms. We have a radius equal to 1.10 meters. That is a radius, even though my R leg is almost horizontal. Okay. It's a vertical circle, and what we want to know for part A is V min, and what we want to know for part B is what is the tension in the rope, B, T equals question mark if, let's say T equals question mark at the bottom if V equals 2 times V min. So that's what we're trying to figure out here. I'm going to say solution. What we need here is Newton's second law. The summation forces in the y direction equals mass times acceleration in the y direction, like that. What we also need is A centripetal, which we'll normally just call A sub c, is equal to v squared over r. And let's go ahead and draw our diagram real quick. So this is the top. Well, that was really a bad looking arc. So this is the top of the motion. This is a mass m. And what we have tied to it is a string. So the forces acting on it are going to be the weight mg and the tension T. Okay. I'm going to assume, for instance, that this is our x-axis and this down here is our positive y-axis. Then I'm going to say the summation, well, let's not use red for this equation. We'll say the summation forces in the y direction equals mass times acceleration in the y direction. And I'm going to draw over here that in order for this to go in a circle, the A must be A centripetal. Okay. Now, according to Newton's second law, the summation of the forces for this part has to be T plus mg is equal to m v squared over r. Now, if the velocity is really fast, then you can see the mv squared over r is going to be quite big, and the mg won't be big enough, so the tension will have to kick in. But that also means that if you sort of skirt the line where mg is just barely enough to produce the pull that you need to keep it in a circle, then that's the case of t equals 0. So what hopefully you realize that we just figured out was that in the case of minimum velocity, the tension goes to zero. So for V equals V minimum, T goes to 0 newtons. So if that's the case, then we can take this and this, in other words, equation above and that equation, and we're going to say mg equals mv min squared over r, or finally we get v min is equal to the square root of g times r, which equals the square root of 9.80 meters per second times 1.10 meters. Notice that gives us units of meters squared per second squared under the square root, so that V min, when you take the square root of it, it's going to come out in units of meters per second, which is exactly what we want. So I'm going to say the square root well, I was trying to find the square root. Oh, there it is. The square root of 1.1 times 9.8, and that gives me 3.28. Now we had 3 sig figs, so I'm going to add one more. 3.283 meters per second is V min. So that's the answer to part A. Everybody follow that? For part B, we have to use V equals 2 V min, which of course is 6.567 meters per second. Now, in this case, we're actually at the bottom of the arc. And actually, I should draw that a little higher because I need the arrows to be down. Okay, but here's our mass, and the forces we have acting are going to be mg acting downward, and then we have the tension in the rope acting upward. But the acceleration for this has to be the centripetal acceleration, and it has to go in the upward direction. So if I were to apply a coordinate system, I would say up is the positive y direction and right is the positive x direction. And now I'm going to say the summation of the forces in the y direction equals mass times acceleration in the y direction. That's going to give me T minus mg. So m, remember, was 0.150 times 9.8 is mg, and that's 1.47. So 1.470 newtons. That's what mg is. Let me write that over here so you won't get confused later. Now, all of that has to be equal to 0.150 kilograms times V squared, which in this case is going to be 6.567 meters per second squared, divided by the radius, which is 1.10 meters, like that. And now we can solve for T, and T is going to be 1.470 newtons plus 0.15 times 6.567 squared divided by 1.1 gives me 5.88. That's 5.881 newtons. And now we're going to add that to 1.47, and that's going to give me 7.351 newtons. is equal to the tension. So that's the tension required by the rope at the bottom. Notice in this case, it's literally the tension's got to support the weight of the object mg, plus it's also got to provide the centripetal acceleration to keep it in a circle. I was telling my class today on this. Back in the 90s, I watched a 60 Minutes program where a guy was doing sort of base jumping and base swinging from various things, and he decided him and his friends were going to get together and swing from the Golden Gate Bridge, which, by the way, is high enough that you can actually die, and people use that for committing suicide. So it was a potentially dangerous thing. He weighed himself and all his friends because they were all going to be strapped together doing it. And just for some examples, let's say he weighed his friends and the total weight was like 1,500 pounds. He went to Home Depot. This was actually part of the story. Found some rope, and the rope was like 3,000 pounds ultimate strength. So that's twice their weight. He said, "Oh, that's good. It got a little safety factor too." But he just didn't understand physics well enough, so he didn't realize that that may or may not be enough. Because when the people swing from the Golden Gate Bridge, they're not only the rope's not only going to have to sustain their weight, but it's also going to have to provide them with centripetal acceleration to make the circular swing. And in fact, they fell about 30 degrees before the rope broke, and like one person hit a boat. That person, I think, became a quadriplegic for the rest of their life, and like couldn't even feed themselves. One person might have died ultimately, but all the people got really badly injured, including the person. And the person that set it all up and didn't understand the physics, but still got the rope and stuff. He was found negligent and went to prison for it. So. There is some danger to not knowing the laws of physics, especially if you're doing, crazy things like that. Anybody have any questions on that? All right. There's a really good conical pendulum problem that I'd like to do too, but I really need to get to the bank curve type stuff. So I'm going on to the next example, highway curves, banked and unbanked. I did a banked one. I think that's really trivial. So I'm going to go ahead and try to do an actual banked one instead of an unbanked one. And that's example 515. Example 5-15. And of course, you can always look at my videos on my YouTube channel to see other examples. But in this case, it says for a car traveling with speed v around a curve of radius r, determine a formula for the angle at which a road should be banked so that no friction is required. B, what is the angle for a road which has a curve of radius 50 meters with a design speed of 50 kilometers per hour? So A, we're saying V is the speed, we're saying R is the radius, and what we want to know is at what angle theta should the curve be banked. And then in part B, we want to know if V equals 50 kilometers per hour and R is equal to 50 meters, what is theta? That's what they want to know. So let me draw a picture for starters so it'll make some sense to you folks. So that's the banked curve, if you will. And I'm going to say this angle right here is theta, and that's what we're wanting to know. Obviously, what you know is this is sort of the car or the Tesla Cybertruck that's had a bad injury, obviously. But anyways, that's sort of the scenario. And what we need is this object to accelerate with AC. And I'm going to draw a free body diagram for that. This is the one case where we work with an inclined plane, and it's not helpful to use a tilted coordinate system. So this is the one time you do not use a tilted coordinate system, even though you're tilting the plane. So what I'm going to do is I'm going to draw a y-axis like that. I'm going to draw an x-axis like this. And then I'm going to imagine this angle right here is theta, and that theta is what we're trying to find now. But the key thing here is we have an object of mass m, which may or may not be relevant, that will be subjected to, in this case, we're actually talking about determine a formula for the angle at which a road should be banked so that no friction is required. We're going to assume that the car is going around and the friction force is actually pulling it from sloping or from going out too far and going over the top of the curve. So with that in mind, I'm going to say that the force of friction, and that's the static friction, is that way. I'm also going to say that the force, that is the weight of the car, mg, points straight down. The normal force, on the other hand, is also not parallel to one of the axes. So this is my normal force. And I would say, since this angle right here is theta, then this angle is also theta, and you can see that therefore this angle is also theta there. So with that in mind, I'm going to put another theta right here, and I'm going to recognize that the normal force has a y component that's vertical, and that y component is given by Fn cosine theta. And then it also has an x component that points in the positive direction. So that one is right here. And this force is going to be Fn sine theta, like that. Okay. Now, the friction force is actually going to act parallel to the surface of the road, but we need the other parts. We need, for instance, to break that Fs into components parallel to the x and y axes. We see that the x component is clearly going to be positive. And notice this too is theta. So this would be the friction force static times cosine theta. And additionally, this part is the friction force static times the sine of theta. So now I can say the summation forces in the y direction equals mass times acceleration in the y direction. In this case, we're not assuming we're going to assume the object's not going to go up and down or switch lanes or anything like that. So the acceleration in the y direction is 0. And what we have is, in fact, the normal force, Fn times cosine theta, is pointing in the upward direction. Then we have minus static friction sine theta, and then minus mg is equal to 0. So that tells us that our normal force is actually equal to mg plus sine theta times fs, all of that divided by cosine theta. So that's what our normal force is. And you can see that the friction force is actually making the normal force a little larger, so that's not that great. But now we need to remember that in order for this thing to make a circle, the acceleration has to be AC equals v squared over r. So now I've got to do the summation of the forces in the x direction equals mass times acceleration in the x direction. In this case, the forces are not that many, and they are specifically Fn times the sine of theta in the positive direction plus F static times the cosine of theta, which is also in the positive direction. And that's all the forces acting in the x direction. So that's got to be equal to mv squared over r. So if we can go ahead and plug in exactly what the normal force is, we can be good to go. And in fact, we can go ahead and say Fs is going to be Fs max, which is mu static times the normal force. Okay, so you see there's a little problem. Specifically, our normal force has a expression. Let's call this equation 1, and let's call this equation 2. The normal force has an expression that's in terms of the normal force, so I can't technically save that. I'm going to take equation 1 now and rewrite it. I'm going to say Fn cosine theta minus. Now I'm going to write in the max formula for the friction, which is mu s times Fn times the sine of theta minus mg is equal to 0. Now you can see we have two terms with Fn, so I'm going to factor those out, and that'll be Fn cosine theta minus mu s sine theta is equal to mg, and that means our normal force is actually going to be mg over cosine theta minus mu s sine theta. So that's what our normal force is. Now I can plug this in. I'm going to call this 1 prime. So this is 1 prime, and I'm going to plug 1 prime into 2. So in doing that, I'm going to say mg over cosine theta minus mu s sine theta. And by the way, this one's supposed to be done without friction, so we can just address that. I'm actually solving multiple problems at once, but we can address this by just letting mu s go to 0, and that'll make this a lot easier. But I'm just showing you in full detail how you'd go about doing it if it did have friction. So let me draw a line here so you don't confuse these parts together. But now I'm plugging this in 2, so that's the Fn. Now I'm also going to put sine theta right there. And then I'm going to say plus mu s times, again, mg, but this time it's going to be cosine theta. All of that's going to be over cosine theta minus mu s sine theta, and all that's equal to mv squared over r. Now, if we assume mu s equals 0, which means frictionless, then we can get rid of all that junk, and what we're going to have is mg sine theta over cosine theta plus this all just becomes 0, and then I get mv squared over r, and you can see that the m's cancel out right there, which actually was supposed to be a red marker, but it didn't happen. So the m's cancel out, and we can see specifically that I've got g tangent theta, because sine theta over cosine theta is tangent theta, is equal to v squared over r. So we can now say that theta is equal to the tangent inverse of v squared over rg. So that's our actual formula for it. And of course, you can use these other formulas to figure it out when you do have friction. But like I said, I just did that to show you that if we had friction, it's not that hard to take into account. Of course, you'd also have to consider there is a chance where you go so slow that you slide down the incline, in which case the friction force would be pushing up the incline, and then you'd have to make your equations for the y dimension and the x dimension for Newton's second law and work that out as well. So you'd end up getting a in some sense, you'd end up getting a smallest velocity and a biggest velocity that you can ride without sliding over the top. Now, for part B, they wanted to know what exactly was that angle. So theta is going to be equal to, and notice how beautiful the laws of physics worked out here. The mass canceled out. That could have been horrible if the mass hadn't canceled out. It civil engineers and transportation engineers would actually have to bank curves based on whether it's a Mack truck or a Volkswagen Beetle riding. But since the masses canceled out, that doesn't matter, and we can just make all the roads the same, and the benefit will go to the Mack trucks as well as the Volkswagen Beetles. So in this case, we're going to say 50 kilometers per hour, but 50 kilometers per hour times 1 kilometer in the bottom is equal to 1,000 meters on the top, and then 1 hour on the top is equal to 3,600 seconds on the bottom. So we're basically going to divide 50 by 3.6. Divided by 3.6 gives me 7.35 meters per second. And that's what we're going to use. So I'm going to say 7.35 meters per second squared divided by 9.80 meters per second times r, which is 50 meters. And you can see we now have meters squared per second squared over meters squared per second squared. I'm going to take 7.35, well, 7.35, and I'm going to square it. I'm going to divide that by parentheses 9.8 times 50, and that gives me 0.108. So theta equals the tangent inverse of 0.1081. Now I'll take the inverse tangent of that, shift tangent inverse, shift answer, and that gives me 6.17. Now we only had two sig figs, so 6.17 degrees should be the tilting angle of that one. Let's see if that's what the... How did they get 14 meters per second? 50 divided by 3.6. Ah, I don't know how, but somehow when I did 50 divided by 3.6, I got 7.35 instead of 13.8. So my numbers are right except for the velocity. So let me fix that real quick. I don't know how that happened. I apologize, but I obviously typed in something. This should have been 13.9. And then if I go 13.9 squared divided by parentheses 9.8 times 50, close parentheses, that's going to be, instead of the 0.108, that's going to be 0.3943. And taking the inverse tangent of that, shift, inverse tangent, shift, answer, that gives me 21.5 degrees, which your book called 22 degrees. So that checks. And that's it. We are done. We have officially finished chapter 5. I will take questions, of course, next time, and I might even come up with another example or so to show you Monday. But the main thing is we're done with chapter 5. I moved your homework. It was due Sunday by 11:59 p.m. I moved it to Tuesday by 11:59 p.m. Just to give you a little extra time, but and also to make sure you had a chance to see me on Monday in case you had any last minute questions before you had to turn the homework in. But remember that next week also includes test, a face-to-face test. So keep up with that. You guys have a great weekend. I'll wait for the last person to leave in case anybody has any questions, but you're free to go. Don't forget to chat me your first and last name if you didn't already.
Um,
Yes.
I was just wondering, when are you going to post the practice for the face to face? Because you said that you were going to set one up because the current ones doesn't go over chapter 5.
Yeah, I thought I already did, but let me double check in case I put it in the
Oh,
wrong
wait, you
place like
did.
you told me.
Just hadn't seen it.
Yeah, I'm going to check it real quick. I think it is. It's under practice tests, and I'm in our course right now. Yes, it says PT 03 first F2F, chapter 1 to 5.
Right.
That's the
Okay.
one.
Thank you.
So, no problem. Have a good one, Colin.
You too.
Really quick,
Yes, Jaden.
did you ever finish the problem that you started at the end of last class, and then you said something about working it out, and then did I miss that maybe?
Yeah, if I remember correctly, I said I would go ahead and finish it, and I did finish it and then posted the video on my YouTube channel. So it's there now.
Okay, that's what I was missing. It's on the YouTube channel, not on the Canvas. Okay, thank
Yep.
you. That's perfect.
You
Thank
know
you.
where my YouTube channel is and everything, right?
Yes, yes, I do.
Okay. Have a good one, ma'am.
You too.
Hey,
Anybody
Professor,
else?
it's
Hey,
it's
Ian.
Ian from yesterday. I sent you a few text messages
Yeah,
back
I
and
was
forth.
just talking about you to my students earlier,
Yep,
in this
yep.
class as well as in my lecture. I'm so sorry, bud. Uh, so you were you able to take either of the online tests?
I was not because as of now I've sent tech support. I sent them a intake form yesterday for my problem,
Oh, gotcha. Uh-huh.
and I haven't heard back from them actually.
All right. Well, what I'm going to do right now is I'm going to go into my modules. Actually, I didn't even need to do that. I was already there, crackhead. Let me kill this right quick. Stop share. Okay. So what I'm going to do is I'm going to go into first off, since you haven't done online test 1 or 2, that means you need access to practice test 1 and 2. So I'm going to go
I've
ahead and open practice test for you as well.
I've done online test 1 and online practice test 1. I just
Oh, you
haven't
did
done
do
number
that.
2.
Okay, gotcha. Yes, I already did make the Ian Mulcahy. I did make that available up till September 1, so you probably got that done. And you said you did do online test 1 as well?
Yes, I got test 1 practice and regular test done.
Okay. I'm going to go to practice test 2 then. And just because of the delay, I'm going to give you more time than normal. I'm going to say Ian Mulcahy. I'm going to give you a due date of, let's say, the 12th, October 12th at 11:59 p.m.
Okay. It should be
And
done far before that. I'm
yeah, I just know we've got a face-to-face test coming up, and this would help you in preparing for that. But just in case you got too stressed, I wanted to make sure you had plenty of time. So now
absolutely.
practice test 2 is available till then for you and you only. Now I'm going to also open up the online test for you and you only, and I'll leave that available for that long as well.
Online test 2, correct?
Yes.
Yes, thank you. Thank you so much.
No problem.
I'm so sorry to like put you out like this
No,
and
that's
to
not a problem.
contact you on a
I'm sorry
weekend.
I wasn't able to get up to you quicker. That's really was crazy. I looked at it and it was like six text messages came all at the same time. I was like, what the
Yeah,
heck?
sorry about that.
No, it wasn't your fault. It was like I said, I don't know if it's my carrier or your carrier, but
Okay.
it's
Okay.
there now, October 12th for you, October 12th. Let me know if you have any problems with it doing that weird thing about saying that you weren't registered or whatever. Let me know
Yep.
if you have any problems with that.
All right, will do. Thank you, Professor.
You're welcome. Good luck, bud.
All right, have a good weekend.
You too. Thank you. All right, that's about it. Looks like no one else is here. So, oh, Ryan's here. Ryan, did you have a question, sir? Ryan might not be here. He's not typing. Oh, you are
Uh,
here. Yes.
mic not working. Anyways, okay. Uh, never mind. I'll
You had a question about one of the homework problems or something?
email. Yes. Was
Oh, my. I see. I saw your message about my mic not working. Your mic is working now.
Oh, it is? Can you
Yes,
hear me?
I can. Yes, it
Yeah.
was the
So
block on the incline
I
adjacent
just
to the
had
wall.
yeah, I just had a really hard time with part B for the block on an incline adjacent to the wall. I don't I tried to use the hints to set it up. Then after I
That was
finished
one
it
of the ones
through,
from one of the practice tests, or was that a problem in the
it
homework?
was the homework problem. It
Okay.
just yeah, I don't really know how to.
Let me see if I can find that particular homework problem and then help you out with it. I assume that would be from chapter 4.
Yeah, chapter 4. It says to find the magnitude of the force that the wall exerts on the wedge. So like there's a wedge on a wall and then there's a block.
Yeah, I think I remembered seeing that one. I just didn't know off the top of my head. Do you know what the problem number was? Problem
Let me
416,
see what it says. I
free
mean, it
body
says,
diagrams, force and tension. Oh, block on an incline
yeah,
adjacent to a wall. There it is. That's a tutorial one. Gotcha. Okay.
exactly. And I don't know if maybe my geometry is just really like poor because I took geometry in high school and I'm like 29 years old now. But
Well,
um,
if it makes you feel any better, I never got to take geometry when I was in high school because I was such a bad student. So, so
yeah,
we
maybe I
have an
wasn't paying
incline.
attention. All right.
I'm going to go ahead and share my screen with you again,
Okay.
and let's see what we can do. No, I want this. Oh, that works. Okay, and that incline was horrible, so let's pretend I didn't draw that. And now let's draw this incline like that. Now that's my incline. It's no, whoa.
I don't think I'm seeing it right now.
You aren't? Okay, I see why. I went to the, evidently it says Williams iMac, but it says Zoom Williams iMac as well. And only the Zoom one works. Okay, so this is a really steep incline. That's not what I meant to do, but that's what we're
Okay.
doing. So there's the incline, and it says block slides down a frictionless incline abutting a wall. Find the force on the block then find the horizontal force exerted by the incline against the wall. Okay,
Yep.
so what we're looking at here is here's a wall, and here's a floor, and here's the angle theta right there. Uh, God, that's such a terrible angle. But anyways, this is a mass M, and it has a velocity v going down the incline. And a wedge with an incline angle theta rests next to a wall. A block of mass M is sliding down the plane as shown. There is no friction between the wedge and the block or between the wedge and the horizontal surface. So what we're trying to do is find the magnitude F net of the sum of all forces acting on the block and that sort of thing. So what I'm going to do is draw a free body diagram, and here's where I get to draw it a slightly less steep angle, luckily. So there's my x-axis, and there's my y-axis, and here's my mass. Now what I'm going to have is, and again, this angle right here is theta. What I'm going to have is the weight acting downward, and that's not parallel to either axis, so I'm writing it black, and that would be mg. And I have a normal force, which acts in the positive y direction. That'll be F normal. And then I have no friction. It did say no friction. Yes, no friction. That should be basically it. Only now I've got to realize that that angle being theta down there makes this angle also theta. And therefore, this right here is mg cosine theta. And then this right here is mg sine theta. That's the free body diagram for the forces on the block. And what they're wanting in part A is to find the magnitude F net of the sum of all forces acting on the block.
Okay, I see what I did wrong. Well, I kind of don't understand why what I did was
Okay.
wrong, but I understand how they got the answer that I eventually got. But I thought like I could just use the current triangle they already had to solve for like the hypotenuse.
Right.
That's the x-axis. So I tried to do like I think it was like mg like 1 over I don't know something with
Yeah.
cosine, but I don't it did not.
Gotcha.
Let me see what I wrote.
Well, one thing to remember, you might not recall this. I've met a lot of students that never got this from trig, but when you
Mhm.
say sine and cosine, the sine of theta is the same thing as cosine of 90 minus theta. That's why it has the word co in front of it.
Okay.
So complementary angles, the sine is the cosine of the complementary angle to theta, and the cosine is the sine of the complementary angle to theta in that sense. So that might help you a little bit. So
Okay.
you can always replace sine theta, for instance, with pi over 2 minus theta.
Okay. So that gets to part A, which I understand. And then part B is where I kind of just started
Yeah, so
not
for
understanding.
part A, the F net, the summation forces in the y direction equals mass times acceleration in y direction. This block is just going to slide down the incline, so the acceleration in
Yep.
y direction is 0. So that means the normal force is going to exactly cancel out the mg cosine theta, but the summation forces in the x direction equals mass times acceleration in the x direction. That means mg sine theta is just going to be equal to ma, and therefore you can just say mg sine theta is equal to F net.
Yep. Okay.
But that's also mg cosine 90 minus theta because of the way sine and cosine are defined. But that's part A. Part B, it says find the magnitude FWW of the force that the wall exerts on the wedge. So what we got to realize is, according to Newton's third law, if the wedge applies a force of mg cosine theta, or mg sine theta, excuse me, on the block, then the block is going to supply exactly the same force, but in the opposite direction on the incline. So the incline is going to experience a force this way that looks like mg sine theta. But that y component of that can't really do anything, but the x component can actually force the block up against the vertical wall, which is what they're asking for. So what we can do is break this force down into a component. This is the angle theta. This would be mg sine theta times cosine theta. And this force would be mg sine theta times sine theta. So that mg sine theta in red is the force that the block is applying to the incline. And then I broke the incline force, the force on the incline, up into a component that's vertical, which means that that's just the force it's applying to the floor and therefore doesn't mean anything. But when they ask, find the magnitude FWW of the force that the wall exerts on the wedge, then you realize, oh, well, the wall's got to do exactly the opposite. So the force
Okay.
is mg sine theta cosine theta. So FWW is going to be actually to the right, and that would be mg sine theta cosine theta. And then you can use a trig function for that. That turns out to be 1/2 of the sine of 2 theta.
Okay. That makes a lot more sense.
Does that make sense?
Yeah. I just need to get better at applying the three laws.
Yeah,
Still,
there's also
still having trouble with
these
that.
identities that pop up every now and then from trig. So if you're not savvy enough to know those off the top of your head, and there's some very specific ones: sine squared plus cosine squared equals 1 plus tangent squared equals secant squared, and then the double angle formula, that's kind of handy, and also the sum of the angles formulas are kind of handy. But that's pretty much all the ones we use mostly. Occasionally you'll have to use some other one, but that should do it.
Okay.
Does
All
that
right.
help?
Well, that helps with that. I emailed the testing center yesterday and they didn't get back to me. I'm gonna call them tomorrow, but that is like the last day I can schedule for Saturday.
Gotcha.
I work 5 days a week. And the military is not very helpful with
Not very
getting off.
conducive. Yeah, exactly.
So if by chance I'm not able to get a Saturday appointment, I don't. I mean, we can cross that bridge when we get to it, but
Yeah, just
it
let me
just
know.
might
Keep me in the
happen.
loop. You might want
Okay.
to try texting me instead of emailing me because texting me normally gets me a little quicker.
Okay. Is your
But if you
number on
run into
the?
that, yeah, it's on the syllabus.
Okay.
I don't want to put it on the recording right now, but it's
No,
definitely on
that's
the
fine.
syllabus.
Okay.
But yeah, let me know if you can't get it, and there might be something I can do. Sometimes I can proctor over the internet if you have the appropriate things. Like sometimes I'll make you
Yeah, I
set up
have
your
the
phone
lockdown
to.
browser, I
Okay.
think.
Yeah, with a lockdown browser, and I can set up the phone off to the side so the phone can see you and your computer screen and your hands and your keyboard. And as long as I can keep that open and you've got the lockdown browser, then sometimes I can even help a student that can't get a proctor any other way.
Okay. I appreciate it.
All right. Have a good one, Ryan. Thank
Thank
you.
you so much.
No problem. Have a
Bye.
good day. All right. So that's it. See you later, folks. Bye bye.